Hello everyone. So welcome back to this stream. So in this stream I have some papers to read like this system architecture papers. Let me share my this one. So I have Instagram system design. I will read this one. Then I have result ORM research. I want to do app backend setup if I get a time or some. Let's see. Let's start. Designing Instagram. So the problem statement is design a photo sharing platform similar to Instagram where users can upload their photos and share it with their followers. Okay. Subsequently, the user will be able to view personalized feeds containing posts from all the other users that they follow. Gathering comments in from the application should be able to support the following requirements. User should be able to upload photos and with the photos they have uploaded. So this will like a profile. You should be able to follow other users. Okay, and the user can feeds containing posts from the users they follow. Okay, user should be able to like and comment on the post out of scope, sending an email, receiving message from other users. Okay, gathering machine learning based personalized recommendation to discover new people, photo, video, and stories. High level architecture. So the high level architecture will be work from client to Instagram server. Then we can manage some graph data store for social like followers management. Then we have a data stream. So we are dumping the data. Yeah, we will create two services that will be user feed service and media counter service. Columnar data store and columnar data store. I guess this one is Kafka or don't know. Let's see. When the server receives a request from an action post like etc. from a client, it performs two parallel operations: persists the action in the data store, publish the action in a streaming data for purpose of model. After that, the various service, example user feed service, media counter service, read the action from the streaming data store and perform the specific task. The streaming data store makes the system extensible to support the user, example media search, index, location search index, and so forth in future. Fun fact in this talk.
It was
So in this talk, Rod Grigo, Director of Engineering at Insta, talks about the different challenges they have faced in scaling the data infrastructure as Instagram. So we have system components. System will comprise of several microservices, each performing a separate task. We will be user graph database such as Neo4j to store information. Is a Neo4j is a graph like database. The reason we chose a graph data modeling in that our data will contain complex relation between data entities such as user posts and comments as nodes of the graph. Yep. After that, we will use edges of the graph to store relations such as followers, likes, comment, and so forth. So let me search in graph. So this line is an edge and the point is a vertex. Okay, so line is an edge and point is a vertex. After that, we will use edge of the graph to store relationship. And additionally, we can use columnar database like Cassandra to store information like user feed, and we have microservice, user feed service, post service, follower service, comment service, media hosting service like service, and data storage we have Cassandra and Neo4j. Component posting on Instagram. Okay. Post media on Instagram. Post service, forward the media content, media hosting service. Upload media file to the file storage file. Then fourth one, return the URL of the uploaded media. Process the media in the graph data store. Okay, push the users post activity in the queue. So from 6 it will move here also user activity service. Provide confirmation that media is uploaded, and here we have this asynchronous, this is a synchronous process, and this is a asynchronous process. This is behind the scene. Initiate the process that process the activity, process the user activity information, columnar storage activity, Cassandra storage, fetch the number of followers of the user from follower service, and we have user is not celebrity, few thousand followers. Trigger the process to pre-compute the feed of the following using a push-based mechanism. User is a celebrity, do nothing as we will use a pull-based mechanism for generating user feed. Trigger the process to pre-compute the feed. Send us from here the user feed service here. And now we have, there are two major processes which gets executed when a user post a photo on the Instagram. First the synchronous process, which is responsible for file storage, processing the media data store, returning the confirmation message to the user, and triggering the process to upload the user activity. The second process occurs asynchronously by persisting user activity in a column data. Pre-compute feed facility. Users have one the process to run after the feed to the other followers. We will extremely compute the occupancy. Okay, so we don't pre-compute feeds for celebrity. Users have 1 million plus followers. As the process to fan out the feeds, all the followers will be extremely compute, and I will say it. So API design, we have provided the API design for posting an image on Instagram. Below we will send the file and data over in one request is a multi-part content type. So actually this should come to this one. Please consult for additional information about file upload and driver quality issues. Alex. Okay, so there's a bit in navigator. Any user with service queue post, the message is added by Twitter. User free service makes a call to the follower service to fetch the list of followers of the user, and after that the post get added to the feed of all the followers in a common. Okay, this is the case. Fetch user post feed, sorry. User feed can send us to the follower service. User to the service and user feed service. Fetch the feed for user from the non-celebrity users. Fetch the last of celebrity of the followers. Fetch the first one is okay. Make the request to fetch the feed. Fetch the feed for users from non-celebrity users. Fetch the list of celebrity the users followers. Fetching the report. I don't know why the quality is such a bad. Okay, so when a user request for a feed, then there will be two parallel threads involved in fetching the user feeds. Optimize for latency. The first thread will fetch the feed from the non-celebrity users, which of all the users follow. The feeds are populated by the fan-out mechanism described in the pre-computed feed section. So fan-out, messaging pattern where messages are broadcasted in one-to-many arrangement. The second thread is responsible for fetching the celebrity feed of the celebrity followers. After that, the user feeds the feed from celebrity and non-celebrity users and return the merged feed to the users requested. The response below can be mapped directly to the graph data model mentioned in the next section. We have a list of feeds: post ID, post owner ID, post owner name, media URL, number of likes, number of comments and comments. Data model graph, we have okay, so we should expect from so name, alias, type regular user, follows Bill Gates, celebrity user, post image URL you are commented on, name Bob regular user, text type comment replied on, likes this one, follows this Japanese celebrity users and comments on this one. We can use a graph database such as Neo4j, which stores data entities such as user information, post, comment, and so forth as a node in the graph. The edges between the nodes are used to store the relationship between data entities such as followers, post, comments, like, and replies. All the nodes are added to an index called node index for faster lookup. We have chosen this NoSQL based solution over relation database. I can provide the schedule to have hierarchies. Okay, which document two level and sequential due to the schema best. So we use graph. The nodes are added to an index called node index for faster lookups. We have chosen this NoSQL based solution of the relation database as it provides the scalability to have hierarchies which go beyond two level and extensibility due to the schema-less behavior. Simple query supported by graph, fetch all for false on JBesos, node index dot user ID for list Bezos followers to array list, relation Bezos for creation, including followers. Start node, fetch all the posts from Bill Gates. We fetch all the posts from Bill Gates on which Bezos have commented. For node Bill Gates post relationship users commented just columnar data model. We will use columnar data storage such as customer to store data entities like user feed and activities. Each row will contain feed activity information of the user, which we can also have a TTL based function to evaluate older code. The data model will have something similar to user ID and list. So in terms of co-infra team has mentioned about how they use Cassandra to solve.
When I found Hostinger and I found out about the website builder, I was really blown away. It made building a website
the job.
I got to know this now and do this. Okay, so streaming data model, we use cloud technologies, Amazon Kinesis and Azure Data Analytics for correctly analyzing real-time streaming data to get highly insight and react to new information. Some of the major streaming post follows. We have optimization. We will use a catch behavior and RU based eviction policy for catching the user feed. For catching user feed of active users, this will not only reduce the overall latency in displaying the user feed to users, but will also prevent decompression feed. LRU based cache for storing user feed of the active users. Another scope of optimization lies in providing the best content in the user feed. We can do this by the one generated after user the last login. For those who the users follow, we can apply machine learning techniques to rank the user feeds by assigning scores to the individual feed, which will indicate the probability of click, like, comment, and so forth. We can do this by representing each feed by featuring vector which contains information about the user, the feed, and the interaction which the user had. People in the feed, for example, whether the user had clicked, like, commented on the previous feed, or whether the story. Okay, so it appends Upgrades are the most important feature of feed ranking will be related to social networks. Some of the key data static to the user close followers. For example, there is close followers of Elon Musk, but another user close followers of Gordon. Whose photo the user always likes, whose links are most interesting to the user. We can use deep neural network, which will take the several features and evidence features which we require for training the model. Those features will be passed through the okay, and will be used for predicting the priority of different events like companies manufacturing this term.
I have been shouting since 2023 that learn chat.
So we have 3 videos in a row: 58, 59, 30. Okay, so talks about the machine learning done to create personalized news feeds. It talks about the classic machine learning approach they used in the initial phase of machine learning news. These all videos to watch. Okay, so we have this I guess I showed you this one. This blog is of 2012. Let's see. So it has a welcome secret, but you may have Facebook. Just what is Facebook? Why is it website? You know, Instagram. Yeah, yeah. Check this article. I call Instagram in the comment description. Stay started there. Little did we know about how truth. If you want to learn about their data and their pictures, just keep it Instagram. Share is a free photo sharing a social network service for your iPhone that has been instant success. Fifteen per seconds, 18%, 50% filter. So, like 14 million users, it just took now 30 million users. They reached 15 million photos in August, while several terabyte of photos, and this with just 3 instances all on the Amazon stack. The Instagram team had written up what can be considered the and then the canonical description of the stage era. What powers Instagram hundreds of instances. Instagram team uses 13 is a small yet has experienced rapid growth. Cutting the best of rising social media movement. It uses a habit of SQL and NoSQL purposes for they shows the cloud over the Colo Amazon services are highly leveraged rather than building them repeatedly. It is so machine work scheduling links component together the system. Don't have to build a data storing memory in the cloud. Most code is dynamic language. Custom bits have been coded to link everything together, and they have run fast and kept small. We will just too long to read the article here. It's very well written. To the point, definitely worth reading. Here is the lessons. Essential lesson and keep it very simple. Don't reinvent the wheel. Go with the proven and solid the engineer. They now reportedly have 13 employees. You know, this was a while back, and now they have Amazon store. They use many of them as with only 3 units, so don't have time to look at the self posting. 100 plus EC2 instant total for various purposes. Ubuntu Linux Nestle all solid other Ubuntu version version of them. Amazon Elastic Load Balancer routes request with the 3 engineers instances behind the EMB SS at 10 minutes. Real age lessons to save you on the engine. Amazon on with the DNS 25 Gen to 25 plus. Hello Ron, by saving mobile data is my passion. Sometimes it helps. By the way, thumbnail कैसा लगा? 25 Gen operation service for high CPU के traffic in CPU bandwidth. It's a high CPU extra large. Unicorn Azure WSGI server Apache. I will configure more. Okay, so this is a Python, so mostly for Django. Came to say good night. Andy, good night, run by. Take care. 12 Postgres replicas and different access and the master. Good night. Thank you for the invitation. EBS is used for snapshotting to the take frequent backup. EBS is deployed at the server to get DADM is a Linux used to manage and monitor software-related services. It is a data stream. It is used in modern distribution plus review portable file system cache diagnostic. It is used to manage what data in memory, especially when failing over from one machine to another. PG bouncer. But I don't know if it will be attached to the HTML front as a CD and Redis power their main feed active session system and other services. Redis runs on the several core extra large amount of range and Redis runs in a master as Apache Sora powered with GeoSearch API like a simple 6 memory instance for caching connectivity using German is used to but German I pronounce it German. German is used to share photos to Twitter, Facebook, etc. notifying real-time subscribers of the new photo posted feed and not only Python work launching tasks for the game task queue for insurance service and so a billion blocks. Monitoring the system and noticing incident simplified website monitoring. This transform your operation and work in agent operations. Ping down can work ping down. Okay. In the operation framework is from out for the machine so that that's what it is. How is it to do work in parallel to loop and simple function. Hello. Let me see how far you are at coding. I do not get what you are saying. By the way, welcome to the stream. Okay, so yes, it's from my thumbnail. Welcome to the stream. Hope you are having a good day.
And yeah, I guess I'll get started, and there isn't much in the introduction. And I think it gives you guys a few extra minutes to get in. Anyway, so thanks for having me here. My name is Rodrigo, Rodrigo Schmidt. I'm at Instagram now. I manage the Instagram data team. I joined Facebook a few years ago, so I'm kind of like a Facebook old-timer. But I came to Instagram about 2 years ago to start the data team. And the way we do data at Instagram is more end-to-end. And by that, what I mean is that we cover kind of like what I call the life cycle of data. So we start by collecting the data from the systems that we have, like from our app. So we collect that, we aggregate. So we do a lot of like processing of the data as well. When you think about like real-time processing or ranking, machine learning, and then we feed that into the product again, and we reuse the data. It could be for analytics or even to build things like Instagram Explore, which generates then more data that you can then collect, and like kind of like you get the gist of it. So when I say collection, you can translate that into server-side logging, client-side logging, database scrapes, data warehousing, data infrastructure pipelines. When I say processing, you translate that into stream processing, real-time analytics, ranking, machine learning, indexing of the data. And the products that we power with those technologies are Search, Explore, account recommendations on Instagram, Trending, which is something that we launched last half, or even the resurrection emails and notifications that we send to like bring more users to Instagram. And it's a lot to cover, and we are quite a small team. So we are about, we started with three people, myself plus 2, and we are now at about 20 in 2 years, and we cover all those things. But I guess like having a small team forces us to be efficient in 2 important ways. One way is that we own the whole stack, like we own, what I said, we own data end to end. And therefore we only build the things that we really need, and we know exactly what we need and when we're gonna need them. And number 2, we can shift resources based on company priorities or like our internal priorities way more easily, just because we own like the whole stack of data. Which brings me to like the theme of this talk, which is like how we are scaling things, how we are growing our systems, how we are growing the team. And before I get to how, I'd like to get into like when and what, like when to scale and what to scale. And which brings me yet another question to answer before that, which is like why to even scale? So I'll address like the those three things in a single slide, and go in order. So why to scale? Well, I like to think that you need to scale something when you're about to have some scaling problems. And by that I mean like your system is running out of running out of capacity, or like you have too much load, or you don't have as many machines, or like you have too many users. Like it's getting to a point that you see some stress in the system, right? And when do you do that? Like when do you take action to actually scale? Do I have to be too proactive? Do I have to be like just reactive and change things, like change when the system is collapsing? And the way like we think about it at Instagram is to do things at the right time. So like we do that when you are about to, like when the problems that you're having, that you start to notice, they're about to hit your users. Like they're about to create like a major issue for your end users. And what to scale, that's much simpler. Like you just look at your architecture, you look at your system, and you find the parts of it that are the most stressed, like the bottlenecks that are compromising like the whole architecture, and that's the part that you focus first. Okay, I think most of you like already know that. So that goes back to like how. That's the recipe that we use on Instagram. It's like number 1, identify the imminent problems that you're about to have. Like identify that, for example, like you're running out of capacity, you're starting to see a spike in latency. Therefore, you know that you cannot take on the load that is going to increase with the number of users that is increasing at the rate that it's increasing currently. So you identify those problems, and then you look into the simplest possible solution that you can implement. And I think that's super important because you don't try to over-engineer like the problem, right? Like the solution. So you just look at the simplest possible way you can solve that issue. And after you solve that, then you can start iterating. So like you solve it like the simplest possible way, and if you see that is not enough for like the long-term future, you can iterate and make it better and make it faster or make it like more performant. Whenever like the environment changes. So if you fix something and then later on you increase your load even more, then you can go and fix it. But don't try to be over proactive on fixing problems that you still don't have. Now I'm gonna like kind of like explain this principle using a number of examples on things that we have done in the last 2 years at Instagram. So I chose like 3 very good examples and like some lessons that you learned along the way with those examples. And I'll start with the basic data infrastructure. So when we started the data team, taking the simple database snapshots was quite hard. So by that I mean like we used Postgres. So taking a snapshot of the data that we have in our Postgres databases and putting it into Hive, like somewhere that we could do some batch processing. That was hard. And that was the way it was being done before. Like I call this the database snapshot v0. So if I wanted to get, if that was like 2 years ago and I wanted to get a database snapshot, that's what I would do. I would start new database instances, like I would start new Postgres instances in AWS. I would load the data from S3, from backups of the master databases. I would export the table data from that those new instances into CSV files, import those CSV files into Hive, a staging area, and then migrate from my staging area into an actual partition that then could be queried by analysts and other engineers. So that was like hard, and it was very slow. It was pretty high maintenance, and like a lot of the process was manual, and it was prone to machine errors. Sometimes like the database would just crash in the middle of the process, and you have to manually restart them, or human errors. Like somebody, like you would forget a parameter in one of the scripts that you had to run, and then all of a sudden you ended up with just half of the snapshots that you wanted. So what we did is like, okay, so like what is the problem? Well, the problem is like this is too much high maintenance. It's taking too much time. It's too slow for the scale that we have. It doesn't get us the data at the time that we need. So we automated, streamlined, and optimized the process. And that was the simple solution that we came up with in the beginning. So instead of using instead of starting new instances every time, we would just use dedicated databases. And instead of like loading backups from scratch, we would just continuously have them load the incremental backups that were being as they were being stored on S3. That in itself helped a lot in the process, and we also optimized steps 3, 4, and 5. We just made those scripts faster and lighter. And once this was done, like we didn't have to care much about it for a while because it was just running smoothly. It was a simple solution. We didn't have to over-engineer it, and then we could focus on other areas that we needed to improve at Instagram. Until we got to this point where some sharded databases, they just became a little too big. Like it was just too big, and we had to have too many like dedicated databases to snapshot those, and that became a little bit of a problem. That's when we switched to something completely new. So we looked into doing like real incremental scrapes, which looks something like this. So we installed triggers on our master databases. We're using Postgres, so like we just put some triggers there, and every time that any row was being updated, those updates were being pushed into a scribe stream. And that data would end up directly in Hive. So we already have like the pipeline set up that we can take the Scribe data and load it into Hive. And from there, we would run pipelines on a daily basis that would merge the incremental data with the snapshots from the day before and create the snapshots for today. That was a completely different system, but that was the best solution. That was the simplest solution we could come up with the problem that we have at that point. And again, like we didn't have to care about it for a while until the whole merging process of taking the data from the day before, like taking the snapshot from the day before and merging it with the incremental data from today just became too expensive. Like imagine, like Instagram was growing from 100 million users to 200 million users, and then from 200 to 300 million users. Those users are taking more and more actions because the time spent is increasing as well. So like the amount of data that you have to process was like increasing exponentially, and the whole merging process became way too expensive. And at that time, so things were not as bad though, because by then we were already migrating a lot of our infrastructure into Facebook data centers, and we could start leveraging on Facebook technologies. So one solution that we came up with there is like completely different from what we were doing before. Is just take the databases that are being problematic, like the ones that are taking like the longest, the ones that have the most data, and start moving those into Facebook data stores. So instead of storing the data only on Postgres, we started like doing double writes into some of the Facebook data stores. And those data stores at Facebook, they already have a streamlined process that takes database scrapes, like database snapshots automatically. So again, like a very simple solution. And it solved the scalability problem because, well, scraping was already in place for that. Another example like of how we evolved our basic data infrastructure is like tracking individual actions on Instagram. What I mean by that is, let's say, like the likes or the uploads that are happening on any given day. So like somebody likes a photo. So you want to track that those actions are happening. You want to know how many likes happen on a day, how many uploads happen on a day. And this was like our V0 again, like going through the whole iteration. So in the beginning, we would run Fab scripts that would collect all our Nginx logs. We would export those Nginx logs into Hive. We would run a Python parser in MapReduce that would just look at the Nginx logs and break down, like if a request is being done to this endpoint, that means it's a like, or if it's that endpoint, that means it's an upload. Based on the parameters, you would see like the user that originated the like and the destination of the like. So we kind of like had to like duplicate the logic of the app in this parser. And that was how we generated like Instagram, a partition with daily Instagram actions in Hive. Worked well when the app was simple and the infrastructure was simple as well. But over time, like as the app became more and more complicated, and like a single endpoint could handle maybe multiple types of requests, like duplicating that logic in the parser became quite hard. And also, like as we increased the number of Nginx boxes from like a few tens of machines to maybe like hundreds of machines to take care of the load that was increasing with the increased number of users, it just became more complicated to run that script that would catch all the Nginx logs and export them into Hive. That's when we switched it to something like different. Our initial proposal was to just, again, like get Scribe supported, something similar to the incremental scrapes. So get Scribe supported in our backend servers. And then every time you want to do an action, you just like log that action using Scribe. But at that point, we had more people interested in, like not more people, but more systems that were interested in reading from that data in real time. There were more consumers of the Instagram action data. And so we decided to go with a different proposal. So at that point, then the problem was bigger than just logging those actions and having them in Hive. The problem was actually creating a pub sub system or like a pub sub architecture that would allow different systems to plug into and read that data and process that data in real time. So what we did was something different. So we got Scribe supported. That was a basic step in our backend servers. And we implemented this Thrift-based pub sub system in which the actions are always specified in Thrift. And whenever that action happens on our server, like the server is processing a request, and let's say it realized that, okay, this is a like that is happening, it will publish that action via Scribe using the Thrift specification. And any consumer can then read from that Scribe stream and use that data in real time. So it looks something like this. So you have your mobile app, and that translates into requests that are being made to the Instagram server. And then the Instagram server will, as it notices the action is taking place, it will then normalize that data and push it into this fire hose, like this, the Scribe stream, that can be read then by multiple systems. So you can think of all the indexes for search actually read directly from that stream. And that's user search, hashtag search, media search, location search. Hive also reads from that stream, and that's how we get the actions in Hive too for batch processing. And even trending reads from that stream, and that's how we get trending hashtags and trending places. And in parallel, we have this other part of the data infrastructure in which, as actions happen, you write data to Postgres, and from Postgres, we have those database scripts that I mentioned before. So this kind of summarizes all our basic data infrastructure. And if you're wondering how the structure of the data that goes into the fire hose looks like, it's something like this. It's all structured data, all written in Thrift. So you specify what a user means, you specify what a media is, what a like event is, and then those are the objects that are then written into that stream and read by different systems. So it's all structured data, so any system that plugs into the fire hose will know exactly how to read the data that is in there. The big lesson here is, again, be thankful for the previous solutions or the previous architectures that you had in your system, but you should not be emotionally attached to them. You should feel free to change them when they need to be changed. Which brings me to the second case study. It's going to be a little faster. It's the account suggestions. That's another thing that we do on the data team. And if you're wondering what account suggestions means, it goes from there's a number of parts of the app that use account suggestions. One of them is Discover People tab that you can go into Explore. It provides you recommendations of people that you might want to follow. And another one is, for example, when you follow somebody, we call it chaining. We present a number of suggestions of people somewhat related to that person that you just followed that you might be also interested in. So those are all personalized suggestions to you. And initially, it was pretty simple. The way it worked, it was just Facebook friends, contacts from your phone, and community recommendations that we would surface in the app. And there was absolutely no ranking being done. That was simple. That worked in the beginning. A lot of the initial growth at Instagram was pretty much organic, and people would just talk to their friends, have you used Instagram? And people would install the app. But with time, we wanted something better. We wanted to power our growth in a much faster rate, and we could only do that with better recommendation systems. So by then, we had the data team, so we had the data, we had the expertise, we had the infrastructure that we were building from case study 1. And what was expensive before became much cheaper now. So now we had the resources to do it. So we started by just adding more sources, algorithmic sources like friends of your friends or like reverse connections. And we added some static ranking. So we knew that some sources were better than others based on experiments, so we just ranked those sources better. That, out of the bat, that provided us with much better results. And we continued to iterate. So over time, we just started to make the algorithm better. And at some point, I would call it iteration N, what we ended up with was a complete real-time machine learning-based personalized ranking system. So much, much better than what it had in the beginning. And way more powerful, of course, with much better results. All written in C++ using Facebook Thrift for the request and response. And a simple way to explain this system to you guys is in 2 phases. You can think of it like phase 1, you fetch recommendations from different sources, like the algorithmic ones, like Facebook friends, contacts, you fetch all those sources. Then you blend those sources using a ranking system. That's that's when machine learning comes into play. And this ranking system in itself might want to fetch more data from external sources. That data is going to be used as features to make even better, to know how to rank better the results to you. So if you want a graphical representation, it would be something like this. You have multiple sources. They feed into the system as candidates. Those candidates get into the ranking system that then might fetch different features. And this is all I/O bounded, written in C++ with a Thrift interface that can then send the recommendations back to your backend servers. Now, the first version of this system, like after we have done all the real-time, all the machine learning, the first version was using synchronous I/O. That was the simplest thing we could do. It's like one thread per synchronous request, fetching the results, waiting on the I/O operation, like the thread would be holding there, and then get the results, close the thread, send it to the request thread that would aggregate everything, send it back to the server. Now it was simple, it was easy. It worked at a low scale for quite a while when we had like very few entry points for recommendations, but it had too many threads. Like that's the problem with synchronous I/O. You're spawning like a new thread every time you want to make a new I/O request. Has very poor performance. Then we iterated and like we came up with a non-blocking I/O solution. Like a single I/O thread can take on like multiple outbound requests. That is good. A single worker thread can handle like multiple service requests. Much better performance. But code reliability, readability, and maintainability suffered a lot. There's this problem called the callback pyramid that I'm going to show in a second. I can show that with an example. Let's say you want to run I/O operation 1, take those results, use as input for I/O operation 2, take those results, use as input for I/O operation 3, take those results, do some processing, get the results back. If you want to do that with asynchronous I/O, you have to actually write a callback inside a callback inside a callback. So as you are doing operation 1, you say when that operation finishes, I want to run this code, and this code has operation 2, IO2, which also has a callback to run operation 3. So something that was supposed to execute in sequence, you're actually stacking it in your code base. It looks horrible. That's when C++ futures came to the rescue. So we started, if you're wondering what C++ futures are, it's an async framework for C++. And I like to think about it as async I/O for Python, or like the async await operations in Hack, if you're familiar with those things. So it's pretty much like a way for you to organize a workflow of I/O operations in your code in a very nice structured way. So what was before a callback pyramid became this very readable syntax using the then operator, which says like, well, you do operation 1, and when that is done, then you do operation 2, and when that is done, then you do operation 3, and when that is done, you run some code. So it's like much easier to understand what you're doing, and you get all the efficiency of doing I/O asynchronously without like too many threads running in your system. So code became efficient and readable, and we scaled the system as well as its development. The lesson here is like, well, scaling. It doesn't have to be like you don't have to like come up with a breakthrough every time. Like it's pretty much an iterative process, right? Like we iterated on that system multiple times to get to the end result, and even after that, we had to iterate again to make it more performant. Which takes me to the last case study, trending, which is something we introduced at Instagram last half. It was a new product requirement. We wanted to show to the community what was trending on Instagram, which hashtags, which locations were trending. And we needed to know like how to identify trends. So like one good example to showcase this here is like take hashtag Northern Lights. So in any given day, you would expect the number of posts with that hashtag would be quite low, right? Because like people might be like posting a photo of Northern Light that they saw like last year or something. But in one day that maybe like the one day that is happening, like the Northern Lights are happening, that day, people are going to be taking more photos with that hashtag. And that's when you see potentially a spike in the number of photos with that hashtag. So what you want to do is identify those spikes and use that as signal that something is trending. Now, if you skip all the data science of this problem, what you end up with is a real-time counting problem. You want to identify like how many posts like are getting a given hashtag a minute or an hour. And we looked into like many solutions for real-time counting services within Facebook in the open source community, but we couldn't find anything that would work at the scale and performance that we needed. We tried, and like we created some internal prototypes, but like they all suffered from one problem or another. So in such cases, the simplest thing you can do is actually build something new, and that's what we did. I'm gonna like explain more or less the architecture of trending here. It's like a multi-phased system. It starts by just reading from that stream of actions that I mentioned in the beginning, right? Like the fire hose. And that contains all the photos that are being uploaded on Instagram in real time. So that goes into a preprocessor that then might read more data that is going to be necessary for the ranking. And it will pass it along to the parser. The parser will identify from any given upload, like which hashtags that photo has, or each location that photo was taken. And then it will shuffle it and pass it to a scorer. So the scorer will then group per hashtag and or per location, will group like how many uploads are happening in like a five minute window. And with that, we can start like aggregating the data and counting it in real time, and we can pass it along to the ranker. So the scorer also know like what the history was for each hashtag in each location, and can do a comparison and calculate how many new posts we are getting compared to what would be expected, and pass that information along to the ranker that then just has to like rank it accordingly. And like, well, this know that the Northern Lights are trending more than, let's say, hashtag love or any other hashtag that you can think of. Now, if you go one step further, if you're wondering, like, well, that's is that all for trending? No, there's more to that. Just to give you an idea that no problem is like as simple as it might look. So even after you are ranking, you still have to serve that data back to the user. And there's another subsystem that does that. So periodically, we are grouping those hashtags and we are storing it in a database. And then since this information is highly cacheable because it doesn't change within 30 minutes of being updated, so we also store it in a cache that is then served by our HTTP servers. So this is how trending works. And one interesting thing is like in each one of those steps, including the last one, like the caching and like storing it in the database, we found and fixed many sub-problems, many scalability sub-problems that we had. Like scaling the parser was a problem. Scaling the scorer was a problem. Scaling like the caching system was another problem. And we had to solve all of them as we were implementing this new architecture, which gets me to the lesson that we learned with that is like scaling is not only an iterative process, but it's also a recursive problem because sometimes you have to scale the subsystem of like the bigger system that you're building. Now, we're getting close to the end, so it's time to wrap up. There are 3 things that I want you guys to remember from this talk, and those are them. So if you're thinking about scaling your systems, or if you're thinking about like scaling your architecture, if you're part of an application that is growing and you're wondering about your future, this is what you need to do when it comes to scaling. Like identify the main problems that you are having, that you are about to have with your growth or with the changes in your environment. And when you identify those problems, you should implement the simplest solution that you can. And once that is working, you don't need to care about it. Focus on the problems that you are having. Don't focus on problems that you don't have. And iterate only when things change. Like if you get more growth, or if you get like if your resources change, or if you lose machines, that's when you then have to think about scaling it again. So if you want more details on anything that I talked about today, we have a number of blog posts on all those topics. You can go to engineering.instagram.com. It's all there, all about trending. We even talk a little bit about search there. You should also feel free to send me a message at rodrigo@instagram.com. I'm happy to also talk to you guys after this talk at the Q&A space. Thank you so much, and that's all.
I one time worked at a job in which I worked 20 hours a week and was paid $50,000. Okay, it was my first job ever, my first full-time job ever. And it was so easy, I could just coast by. I have never had more burnout in my entire lifetime than I did at that job. It was the least I worked and the most I was burnt out ever. You cannot equate hours worked with burning out. They're just simply different.
Once everything's perfectly organized, I'll start working on my thesis.
Learning Tailwind is essentially just installing it, typing in what you'd guess the class name will be for something, and guess what? You're probably right. But there's some hidden gems in these docs, which I learned far too late. Let's have a look. So first up, we have Divide. Divide allows you to style borders between multiple different elements. An example of when this could be useful would be something like this. So I have this button group with 3 separate buttons, and I want to have borders between each of them. Obviously, I could go through and just add a new border to each one of these, but that would be tedious because whenever I wanted to add a new button into this button group, I would have to add another border as well as consider whether or not I want borders on the edges, and it just gets a little bit annoying. So instead, what I can use is the Divide utility. So I'll just come up to my main div up here and add a divide on the x-axis as well as a divide color. So mine is divide violet 600, and saving that will give me an output that looks something like this. So next up we have scroll snap, and scroll snap actually allows you to dictate how elements are snapped into the container whenever you're scrolling past them. As an example for this, I just have this scrolling carousel right here, and we'll see that anytime that I try to scroll just a little bit outside of one of these images, it's going to snap back to the center of my carousel. Taking a look at what I have in my code, I just have this wrapping div with a display of flex, a width of full, and then an overflow x of scroll, and then inside of that a number of divs inside of it which also have images inside of them. And I've added a snap of X to the containing div as well as a snap of center to each of the individual divs inside of it. And that's what actually gives us the center snapping behavior. You can also do snap start, snap end. I'll allow you to play with that, but for now, now let's move on to the next topic. The SR only utility class allows you to hide elements from the screen without actually hiding them from screen readers. An example of when this could be useful is something like this. So I just have this mock-up little navigation bar. I have 2 buttons on this for like settings and user, but there's really nothing in this that tells a screen reader, hey, this is a settings button and this is the user button. So what we could do is actually add some text in here to label what these buttons do, but I don't really like how that looks. I would like to have this label, but I don't actually want to show that on the screen. To fix this, I'll add the SR only class. This is going to actually add all of these different styles to hide this element, and that'll leave me back with just my buttons, but we'll actually keep these spans in here for labeling purposes. This next one's honestly just basic CSS, but I feel like I never knew this before for whatever reason, so I'm going to show you here. And that is accent color. By default, styling for different form inputs like checkboxes generally have something like this blue color or whatever is default for your browser, but you can actually style these by adding an accent color. So I have my checkbox input here, and I'll just add an accent of violet 600, and now we'll see that whenever I click on my checkbox here, it's actually going to be styled with that color. For the next one, I'm actually going to show 2 separate classes because I feel like I often use these together. The first is outline, which I'm sure you've seen before. You can just add outline to different elements, but you can also style the caret element of an input. To show this, I just have my basic little text area here that I can type stuff into, and I don't really like this blue border caret element of an input. To show this, I just have my basic little text area here that I can type stuff into, and I don't really like this blue border, so I'll fix that by adding an outline of violet 600, and now we'll see that that's styled. But you can actually also even style this little blinking cursor right here using the caret class. So before my outline, I'm also going to add a class of caret violet 600, and if I zoom in, we should now see that that matches my style as well. Next up, we have gradients, which I'm sure you've used before. Or the basic syntax for gradients is just something like background gradient to direction, and then using your from and to colors to actually set the 2 different colors you want in your gradient. For my example, I have this basic little gradient that looks like this, and you can actually add in a third center color to your gradient using the via class. That'll end up looking something like this. I know this gradient is ugly, don't judge me, but you also even have controls over where these stops are positioned like you would with a normal linear gradient. And to do that, you just add percentages with the same prefixes. So something like from 30%, via 70% to 90%. Saving that, we now have an output that looks like this. Next up is animations. There's a number of these that come out of the box with Tailwind CSS. I'll let you play around with all of the specifics of these. The one that I find myself reaching for more than others is this animate ping animation. Super useful for things like notification icons, something like that. But like I said, there's a handful of these, so just type in animate dash with your autocomplete and you should see what the options are. And last but not least, we have space between. Space between actually allows you to get something like the grid or flexbox gap property, but without actually using gap, it just automatically applies the margins for you. An example could be for something like these pieces of text. I have 3 separate pieces of text, this heading, this paragraph, and I just want to have some even spacing between all of these. So I'll just go up on my wrapping div and add a space on the y-axis of 2. That should then give us some kind of output like this, and we can adjust this now as we see fit. So maybe I want a little bit more space, I can go space Y4. You could do this on the x-axis as well. Obviously, this is not going to add anything for me because everything's on the y-axis, but I think you get the idea. All of the code for this will be in the description.
need to plan and need to have a plan for this. So we'll do this off stream tomorrow and start coding with this one from tomorrow night. So we'll end the stream. Thank you everyone. So what are so thank you everyone for watching. Bye bye, good night. Have a good night.